We discussed last time several things, mostly related to chaotic situations. Namely, we said that when we have dynamical system with a particular trajectory in multidimensional space, we have trajectory x of t, we can look at some function of x of t and form what is called a correlation function. T may be both discrete and continuous, that doesn't really matter. And some function g of x of t plus tau. This brackets means time averaging. And we subtract, if they were completely uncorrelated, if probability to find the system at a given state at this moment is completely independent of the probability to find it here, then we have, it will be simply a product of the averages, so it makes sense to subtract the product and call it, sometimes one subtracts and sometimes not, but it's a matter of convention, of course. But basically, the memory of the system is measured by this function. If the system has finite memory, then like harmonic oscillator, it remembers its initial condition all the time. You will have some non-zero result for any t. In fact, in harmonic oscillator, you can calculate it and you will find that f is simply oscillating function. But in chaotic system, it's more or less definition, f tends to 0 as tau goes to infinity. And we said that this property is called mixing. And the true dynamical system, which we describe usually using statistics, like gas of particles and so on, they all have this property, although to prove it sometimes is quite difficult. Typically, mixing arises when you have exponentially diverging trajectories. Of course, you will also have exponentially converging trajectories, but what you are interested in is this exponential divergence and simultaneously compact configuration space or phase space, doesn't matter here. So they diverge. On the other hand, they don't have much place to go. So as the result is chaos. So we saw that in some simple models, I was able only to describe the simplest model with motion on a circle. In fact, it's much more could have been done, but I would need another semester for this. All right, and then we also looked at the theory of turbulence, which also is characterized by the correlation functions. Slightly of the slightly different type, but basically, when you have turbulent flow, the important idea, I'm just repeating what I have said, but that's important. The important idea was that we do have the Navier-Stokes equation. Nobody doubts that it describes turbulence. However, if we're simply looking at the particular solution of this equation, it doesn't really make any sense because it's unstable under small perturbations. If you change just a little bit initial conditions, you have exponentially different solution at the end. So it's not a thing which you can calculate or compute the same instability will, of course, make the computation impossible. So instead, the stable kind of things are the correlation function. And generally, I'm slightly changing what I said. The general correlation function in the steady state case, there are, of course, many other cases, but the simplest case of turbulence is that you generate it by some fan or atmosphere generated by itself. And then you create various perturbations, and when they reach the picture which we described last time, that you generate a big vortex, it decays onto small vortex. So each moment of time you find those vortices, or not necessarily vortices, some perturbation, let's say, of all scales, and the smallest, and energy is transferred, constantly transferred from large to small. And that was the Kolmogorov cascade I described last time. I will not probably repeat it, but important thing is that the correlation function in this case will, with good approximation, independent of time. They will depend only on it's not to say, of course, not at all, that the only such correlation functions are interesting. In principle, the most general correlation function will have T1 here, T2 here, Tn here. So, but the simplest ones, you see, the problem is hard enough to look for the simplest possible objects. And those correlation functions are, although it's not also kind of a not really proved mathematically, but it seems very, very likely, people believe it, that those objects are stable in the sense that if you change the condition, for example, you are sitting at the waterfall and then you move some rocks a little bit, the flow changes, the correlation functions will change just a little bit. There is no instability with respect to. And as I said, we have the set of correlators which depend on x. We derive the set of equations, the equations for these endpoint functions. We derive it by requiring that time derivative of this thing is 0, the steady state condition, and using the Navier-Stokes equation. That gives, in principle, the closed system of equations, but these equations is a mathematician's nightmare, because it's a set of infinite set of correlation function. You cannot really rigorously derive the closed equations for, say, two-point function. Two-point function will be connected to the three-point function, 3 to the 4-point function, and so on. So people nevertheless manage to find some what is called closures by expressing in sometimes in an ingenious way the 4-point function, for example, in terms of the 2-point function. So there's a lot. There are much more ingenious approaches to this problem, but generally speaking, the developed turbulence is an open problem, as I said, and
excuse me,
yes.
When you're talking about correlation function, what are you averaging over here?
I'm averaging over time. what you do, it's not literally how it's experimentally done. Experiments in atmosphere are done differently, but I don't want to go into this. But in principle, you do the following. You have some measuring device, and here at the point x1, another measuring device at the point x2, and you measure each second, you measure the velocities here and here, multiply it, and then average with respect to time. Okay, now, so we leave it at that. I just maybe repeat how beautiful this Kolmogorov picture is, even if it's not completely correct. Which reminds me of the phrase by the another great mathematician, Hermann Weyl, who said that in my work I had a choice between correct and beautiful, I always chose beautiful. Anyway.
Just one more thing. If you're averaging over time, why is the correlation function time dependent?
It's not time dependent. It's just that's basically the point, that it's time independent. You do averaging with time, you obtain a time independent object. And now this object must satisfy certain equation. This correlation function, they satisfy, if you must have ddt equal to 0, and from that follows the...
I thought it was some equal time correlation.
It is equal time correlation function, but how you define it? You have time, and then you integrate dt1 and that's what you call the time average. Okay, so as I said, in practice it's done differently, but it's too long to explain. But there is there is a huge amount of work which is going on presently, in which people numerically and experimentally determine the properties of those correlation functions. And they, as I told you, in the 1990s, they discovered experimentally that there are some deviations from the Kolmogorov scaling. All right. Now there's another nonlinear phenomenon which we will discuss today, and this is the phenomenon. Well, it's again a very wide area of research which goes on right now. It's solitons and integrability is the general topic. So what is the, let me, solitons or solitary waves, they appeared in physics even in the 19th century. The point of the matter is that when we talk about the usual waves, linear waves, they are characterized by some dispersion relation, as we discussed, which depends on the wave vector. I'm reminding you, I will spend 1 minute to remind you something you know from elementary physics course. The amplitudes they are usually presented as a superposition of different waves. And such integrals have a very interesting property. First of all, I just will need it, and so I assume you know it. It's considered as a reminder. First of all, the property of Fourier integral is this. If you have some function c of k e to the I kx, and c of k is some kind of bump, whatever, of the characteristic with delta k. For example, although it's it's absolutely not necessary, you can consider it as a quadratic Gaussian thing, like k minus k0 square divided by delta k square. But that's not the concrete form is useful for you to get to just see how it works, but it's not really important. Then when you take this integral, you get the amplitude which depends on x, and it also will be kind of a bump. And there is what is in quantum mechanics called uncertainty principle, and in classical physics I don't know how it's called, but in any case delta k delta x is of the order of 1. You can very easily calculate. In the Gaussian example, you simply do the integral exactly and see that you have again Gaussian after Fourier transforming become Gaussian again, and that's the basis of the uncertainty principle. In quantum mechanics, you interpret the wave vector as a momentum, and so on. All this stuff is widely known. Now, another piece of more, maybe slightly less known, but I assume slightly less known stuff. Let's suppose that we have this integral. Then suppose we are interested in the asymptotic behavior when t goes to infinity. Then such integrals will be dominated by the points where this phase is extremal. If the phase is not extremal, then oscillations damp the integral. And there's the method for evaluating the behavior of such integrals, which basically says that if we extremize this phase, what do we get? Extremize with respect to k. And let's forget about this factor at the moment. Then what can you say? Which k will be dominant in this integral? You see, when you have an integral or oscillating and so on, you always can find, not always, but often can find a particular domain of your variable which contributes contributes most to the integral. And in the integral, when you have large exponentials, like for large t, you have large exponential behavior. So you have to extremize this. So when it's a general rule that if you have integral over any variable, look for the solution of this equation. It actually equivalent to transfer to geometrical optics from wave optics to classical mechanics from quantum mechanics. But all this is an important thing. I want you to recognize what the extrema of this exponential mean. So don't be afraid of the integrals or anything else for that matter.
So just take ddk of the exponent.
Yes.
So that's your-
So if I take ddk, what I get?
x minus.
Okay, and this is something I assume you know very well. This is the group velocity of the wave. So it tells you that the bump, the maximum, moves with a group velocity, omega of k. Now, the key point is that the linear waves for which this is a solution of some wave equation, actually spread out. If you have, and that's what all this discussion I started has the goal to show you how the spread out happens in the linear case. You cannot have in linear equation a solution which is localized and remains localized. Well, you can, of course, derive it from exploring the integral, the fact that they will spread. I will do it differently. I think in many textbooks you will find, well, I don't know, maybe you will find the treating of this integral. To find the spreading, you have to expand to the second order in k and so on. Instead, I will simply tell you that we have the characteristic size of the bump, delta x, will be of the order delta v, if we have various velocities, multiplied by delta t. It's just the spread due to the fact that we have different velocities. But different velocities are just omega double prime of k multiplied by delta k. So you can write it down as omega double prime of k delta t delta k. But delta k is of the order of 1 divided by delta x. So the result which I wanted, which follows from this very simple analysis and which can be confirmed rigorously by the studying of the integral, for which I don't have time, you see that delta x square, delta x, the absolute value of delta x, grows with time as square root of omega double prime of k multiplied by time to 1/2. So if you have the originally localized bump, then it spreads out like square root of time. Its size goes larger square root of time, except in one case, which we encountered, in which case the spreading doesn't happen.
Omega k is linear in k.
Yeah, if omega is linear in k, and that's precisely the case in one-dimensional sound, but that's a very special case. General waves are always spread out. Except sometimes they don't. And they don't, there are non-linear effects which can prevent them from doing this. And according to the legend, it was discovered in Cambridge. In Cambridge, there's this river Cam, and the students go, I think it's called punting with big poles and so on. Quite interesting to watch. In any case, in the 19th century, it was noticed that sometimes they create a wave which doesn't spread out. And it just propagates, but keep its shape. And later such a wave got a name, a solitary wave or soliton. And the theory of soliton begins with what is called Korteweg-de Vries equation, or KdV. I shall explain it, what this equation is. It is derived from the Euler equation for the case when you have shallow water. I will not go, again, those details are not very interesting, but you can find some of this stuff you can find in Lattice, who treated both shallow water waves and deep water waves. You have just shallow water, and shallow, by the way, and because of gravity, the source of this wave is gravity. Is the fact that you have gravitational attraction. So sometimes they're misleadingly called gravitational waves, but it's not the waves which were recently discovered by. Anyway, well, you can actually try to figure out what means shallow and what means deep here, but I think I will not go into that. All right, the Korteweg-de Vries equation, I think I'm not sure of my spelling. Describes those waves in nonlinear regime, and it has the following form. The velocity of the wave, it's one-dimensional, so this is not surprising term. This is something which we looked again and again and again. Plus, there is a term with a third derivative. And I repeat, it's derive this equation from the Euler is not a big deal at all. It's very simple, and you will, if you read a few first paragraphs of Lipschitz, you will see how it's done. But the equation itself is another matter. It's fantastic equation. It has quite a fascinating property. So we have to so this is KdV, and remember we also looked at a similar equation, which is called Berger's equation, which is that we discussed when we looked at the structure of the shock waves. And these two equations are drastically different. This is much more interesting equation, but I'm not. That's not my point. Can you say what is the great difference? They obviously must have totally different physics. Why it is so different? Why I'm saying it's so different? Think about symmetries of these equations. What can you say? Especially think about time reversal symmetry.
So all the derivatives are odd in the KdV equations?
Yes. So here you have the symmetry here is t to minus t, x to minus x. Or, no, sorry, I'm wrong. T to minus t and u to minus u. and x to minus x. In this case, well, I think I made a mistake here again. We do need x to minus x, yes, or all right. This guy changes sign. If we keep u, so with this, without this term, we can have t to minus t, x to minus x, and u to, okay, there should be u should be unchanged. Now, which is basically the important part is that it's time reversal invariant, and moreover, as I will tell you, it's a Hamiltonian system without any dissipation, while this term is simply a dissipation. You can see this also, the simplest way to see this is to look at the linearized version. In the linearized version, what will be the dispersion relation here? Let's compare the dispersion relation for burgers and for KdV. What is it? What is it in burgers? What is omega of k? You drop, yes. So this term gives you what when you substitute the Fourier decomposition?
Omega u.
Yes, it gives you I omega, while this gives you nu k square. So it's I nu k square for burgers. And you see that the frequency is imaginary, which means that in this case it's not an instability, it's just you have damping. It's just you have friction, you have viscosity, and things damp.
Sorry, I don't understand why the middle term doesn't contribute.
Oh, you consider linear waves. It does, of course, and we will be discussing these terms. But you begin the analysis from the small amplitude analysis, when you can drop all nonlinearities. You drop these nonlinearities, and you get this, and you see that actually, unless you have a shock wave, the more you wait, the better your approximation becomes, because this formula means that u goes like e to the minus nu k squared t. So it exponentially goes with time, decays with time. Something completely different here with KdV. You see there is no imaginary, the imaginary unit disappears, so it is simply k to the cube. And indeed, it's non-dissipative system. It's a Hamiltonian system. Now, let's find the simplest nonlinear solution to this system, to this equation, which describes the solitary wave. It's again still elementary exercise and very simple. Well, we will be looking for the solution, for the special solution which moves with some for the lump moving with some velocity. So let's consider this one function of one variable. let's plug it into the equation, and we get the following. We get f(x) from the second term. We get fxxx here. And what's important, we get f prime. I will change my notation. I will call prime the derivative prime. So the time derivative is simply ut is simply minus vf prime. So as a result, I have minus vf prime plus f. This I shall write it down as 1/2 f square prime plus f double prime prime. And this should be equal to 0, which is to say that f double prime plus 1/2 is equal to the f minus 1/2 f square. Now, what analogy I can use to describe? First of all, of course, this equation is easy to solve. The completely trivial solution, but what analogy should I use to solve such an equation? Where else we actually have the same equation? It has the form of something very, very fundamental and elementary. In which equation which equation starts with second derivative?
Harmonic oscillator.
Huh?
Harmonic oscillator. So
Not only harmonic, any Newton equation begins with. So what it tells me is to write it down as a gradient of some potential. Then it will be the Newton equation. The potential is 1/6 f to the cube minus 1/2 df square. And of course, now you have conserved energy and all this stuff, and I shall leave this elementary algebra for you to do.
What happened to the? Do you pick up a constant when you?
Yes, you are right. I should very good. I should write down this as a when I write it down. It should be not. I should, in principle, as you said. Let's see. Now, this constant will be dropped for the very simple reason. If we want to can you figure out the reason why I want to drop this constant? Remembering physics, not mathematics. I want to describe this solitary wave. What does that mean? It's very solitary. Yes?
It doesn't matter where its displacement is relative to.
Yeah, it's actually right. It's you have to impose the condition that at infinity it's solitary wave, it's localized. At infinity it's 0. So the constant must be 0. And in any case, you see from here that the amplitude of this lump is proportional to v. And if you solve this equation, you will get a very simple solution up to some coefficients, which I will not try to reproduce. You have some v factor divided by cosh square of some factor x minus vt. And this is the exact solution of which describes, you see, very well localized wave. it is moving, it is not spreading. This is some constant here. And another interesting feature is that specific feature for this. You see that if V is equal to 0, the amplitude is 0, the amplitude of lamp is 0, and my interpretation of it is that solitons, KdV solitons, not all solitons, are like sharks. You know, a shark can breathe only when it moves. It cannot stop. It is just so is the soliton, and so far it's kind of 19th century analysis. And now I'm coming to the really modern stuff and fascinating stuff which is hidden there. By the way, there are plenty of equations and physical situations in which you have various localized solutions. So solitons in general, we encounter in all parts of physics. There are optical solitons, there are plasma solitons, there are solitons in particle physics, in superconductors, everywhere. It's a very typical phenomenon. And in the so they appear not only as a result of shallow waves, but also in plasma physics. And in the middle of 1950s, people here in Princeton actually started some numerical work without knowing that it will lead to a revolution. And they did the following thing. It's a group of people. The main author is Martin Kruskel. They simply did a very similar numerical simulation. They have they looked at soliton at the initial moment. They looked at two solitons coming together with some velocities. And they expected basically that when they collide, they break down, all energy will go to some small waves, to some, and that's what they wanted, but that's what they expected, but that's absolutely not what they observed. What they observed is that solitons came together, they stayed together for a while by oscillating. It's this state is now called breather. And then, so there is some oscillations here, and then they go like that, completely intact. And then the interpretation of this fact, actually you can try also three solitons colliding, but in all cases the asymptotic behavior, if you had at minus infinity in time, if you had any collection of solitons, you will have a somewhat different collection of solitons at the end with the same, they will never be destroyed. And now I will tell you about the interpretation of this. Actually, that was a revolution in mathematical physics. They made maybe the most important discovery in mathematical physics of the 20th century. Namely that there are plenty of physically important equations which are completely integrable. And so not only the KdV equation is Hamiltonian equation, it is completely integrable equation. There are non-trivial integrals of motion, and that conservation of these higher integrals prevents solitons from destructing. So and that's what the outcome was. And what I want to do now is to tell you the basic idea of the method, absolutely ingenious method to how to find those integrals, those solutions. It's now a huge area of mathematical physics. Well, it's very the basic idea of the method is that they managed to well, how it happened, I actually asked Martin Kraskell how they came to this. As you see, it's the method. I will simply tell you the way they did it, not with some improvements. They said that suppose we have an infinite matrix L, and let's consider the following equation, which is known in quantum mechanics. So L dot, it's a commutator, ML minus LM. So let's consider, forget about all those equations. Consider matrices. Say n by n matrices. And consider this equation. And then they notice that, so L is a matrix and its elements depend on time. They notice that the equation KdV and many others can be written in this form. It's not supposed, I shall clarify this and make it absolutely concrete in a moment. It's a concrete calculation which is needed to check that the equation is can be written in this form. But and we will, and if it is written in this form, if it can be written in this form, then you have infinite number or large number of integrals of motion. Because what would be the, if you have a matrix like that, suppose you have a matrix equation like that, what would be the conserved? Give me an example of something which will be time independent. Some combination of matrix elements are obviously time dependent, but give me some simplest combination of matrix elements of L which will be time independent. Notice that if you take a trace of this equation, trace of the, under the trace matrices commute. Or you can also say that by, in this case, the integrals of motions are eigenvalues of this matrix. The thing which should be totally mysterious by now is how it is related to this to those equations. It is slightly more, well, I will give you first a very simple example of this. Let's suppose that L is equal to the operator ddx, and M is equal to U. The commutator, we define the commutator in the following way. It's very simple, primitive example. Oh, actually, I want it in a different way. And this is ddx. The commutator of these two things is what? Commute u and the differentiation operator. U depends on x and t. To commute, you do the following. You take a test function psi, and you say Lm is the u d psi dx, ml applied to the test function is d dx u psi. And so what is the commutator, this and this?
Minus u prime.
Yes, so you have the commutator, which is minus u prime. And this equation, it gives you the, it reduces to the equation, to a very trivial equation, du dt plus du dx is equal to 0. So in this case, those simple differential operators produce the linear equations. Not very interesting. It does have infinite number of conservation laws, but it's rather trivial. Now, the way to get the KdV equation, which was discovered by Kraskal et al., is the following. I can't really explain how this idea came. Well, I can try to explain how this idea came to the mind. But let's try to do the same thing, the same game, but with a slightly more complicated operators. So let's take L d2 dx square, the second derivative, plus u of x and t. Where this operator appears in physics? Yeah, it's Schrödinger equation where t is a parameter of the potential, or time, you can consider it as time. And let's try to adjust m, just as we did here. Try to adjust m in such a way that you will get the, when you commute, you will get this KdV equation for u. Here we got this trivial equation. So they started experimenting with various m. It's clear that since in KdV we have a third derivative, it should contain some third derivative thing. And indeed, if you look at this when you have, you will have the equation on the left-hand side, you have u dot. On the right-hand side, you have to do the work and commute those two guys precisely in the same way as I did here, and that will give you qxxx. It's not something, by the way, it's not something usually I ask you to do it in your head, but it's something which requires real work. And the miracle is that for arbitrary operators, their commutator will be operator again. You see, what happens here is that L and M are, generally speaking, contains derivatives and so on, but their commutator contains just multiplication, the function u prime, which multiplies the test function. Well, generally speaking, you would expect that you have not simply such terms, but also terms containing d dx. For example, if you commute d2 dx square with u, it is for that you have to write down d2 dx square u psi. You introduce the test function minus u d2 psi dx square. So you get two. You do get u double prime plus 2 u prime d dx applied to the test function. So when you compute this differential operator, you see what happens is that you cannot write down this equation anymore. It will not be consistent because you have this term which remains an operator. And miraculously, all such terms, which when you start calculating, you will get plenty of such terms. But they all cancel. And the result is this equation. I shall give you one more, maybe more finite dimensional example, because I started with finite dimensional matrices, and this is infinite. It's clear that you can interpret ddx as a matrix, but infinite dimensional matrix. There are two miracles. First of all, that for the KdV this representation works. That KdV can be written down as L dot for these guys. You get KdV equation. And as I said, it's highly non-trivial that this equation is consistent at all. Because if some derivative were left, then we couldn't get it. So first miracle is that you can write it down this way. From here, you can immediately calculate all higher integrals of motion. I'll show you how. It's basically the integrals are trace of quantities like that. This generates commuting conserved quantities. But even more surprising is that there are hundreds of equations important in physics which have the same property, which can be written down as this commutator equation, sometimes called Locke's equation. To make that, of course, was discovered later. And you can actually, so far I just gave you the conservation law derivation, but as you can guess, people developed this formalism in such a way that they now can really describe analytically this collision of solitons. They can actually solve the problem practically of this nonlinear problem is explicitly solved. All these breathers which you get when two solitons collide, they have analytic description which you get from here. But before I go further, I want to give you the discrete version of the KdV, which appears in, again, those equations appear in several fields. Originally, they appear in material science. It was describing propagation of dislocations and so on. And this is what is called the Toda lattice. I mentioned this thing. It's very simple Hamiltonian. And it's, of course, very, very simple to write down the equations of motion. They will be simply, the Hamiltonian equation will be simply P Pn is equal to xn dot, and xn and Pn dot will be equal to e to the xn minus xn plus 1 plus something like that. That's quite obvious. Slightly less obvious, that's what Toda discovered, was that there is a soliton solution to this equation. And again, to find a single soliton solution is not too difficult. You just assume that you have some function you replace, just as for KdV, we replace this by the function f of x minus vt. And that's, so the solitons can be found. And then, once again, the numerical results show that the solitons are indestructible. The question is now, can we have a commutator representation for this? And it will be slightly, first of all, this you can show by some, again, not some elementary procedure, that it's the discrete version of the KdV equation, that if in the longer wave limit you get from this equation, you can go to the KdV. Now the matrix representation of this equation, see how it's wonderful. We are solving purely classical problem, and the only way to solve this problem is to use quantum mechanical Schrödinger operators or their discrete analogs. So I shall tell you how it's rather easy to find L and M in this case. Let's take L in the following form. It's a symmetric matrix plus En delta Nm. I shall write down this thing, and then you have An delta N plus 1 minus An delta N plus 1 N. Now, so what kind of matrix is this? Can you visualize where are non-zero elements of this matrix?
So M is just one off diagonal.
Exactly, yes.
L is
Yes.
diagonal.
Exactly. So we have for L, for example, we have the following. We have B1, A1, it's symmetric. Here we have B2, and here we have zeros. Now we have here 0, here A2, B3, and so on. So indeed, you have the diagonal terms and two lines near the diagonal. And what I said about it's actually you can when you start the key point when you try now to write down this equation that you will that the matrix. You see, what you need is that after taking the commutator, you obtain the matrix of the same kind. You see, with only diagonal and two adjacent lines of non-zero values. Otherwise, that's because L dot is AN dot multiplied by this AM dot and BM dot. So we have on the left-hand side, we have terms like AN dot, delta n plus 1m, and so on. But when you multiply matrices, you can get delta n plus 2m, so you can get further from the diagonal. The small miracle is that it doesn't happen. When you calculate the commutator, you now can proceed calculating the commutator and see that ml minus lm has the same structure as this one, and the equation, which is equivalent to this equation I wrote down, will be something like that. It will be Pm dot an square minus an minus 1 square, and so on. And after trivial change of variables, it reduces to the original Toda equation. One more comment here is that how it's related to those differential operators. The things like delta n plus 1m can be viewed as an operator. If you apply it to the test function, you get psi n plus 1 out psi of n. But psi n plus 1 is e to the ddn psi n. Is this formula obvious to you? How would you prove this statement? So instead of using Kronecker symbols, I could use this exponential of differentiation. And the continuous limit will be simply expanding them, the exponential. So how would you argue that this is true? Well, you suppose that you expand it in Taylor series. So it's the differential operators, which I actually introduced in the continuous, have just this origin. With this notation, by the way, it's convenient to you see what's happening. If you write the L operator in these notations is A e ddn plus B plus e ddn A, and M is A e ddn minus e ddn A. And when you start commuting, the danger would have been if we get, what does it mean in this notation to get off-diagonal terms? Well, it will be meaning that when you multiply it, you will get, for example, e2 ddn. But in the commutator, it all vanishes. And so all that remains is the same type of terms. And as you can guess, people invented many ingenious tricks with this system. They are practically solved explicitly. Now, by the way, the way to obtain this differential operators for KdV is just to expand these things and then establish the connection. All right, this plays a very important part in physics. And you also, one more question. You see, it seems at the first glance, that we get too much, because this equation means that trace L to the k for any k is 0. That's a trivial relation which follows from the commutator. But complete integrability, we must have, in complete integrability, we must have the same number of integrals. If we have n points, we should have the same number of conserved integrals. And here we have more. It seems we have too many. What's the resolution? What do you know about matrices? And
so they're like, since it's one off diagonal, if you raise it to the nth power, it becomes 0.
well, actually, there is a statement in the theory of matrices that all you have independent L to the n, but Ln plus 1 will be expressed in terms of the lower L to the n. So what is really, basically, it simply, this simply says that if you go to the that it's the eigen, you have n eigenvalues of these matrices, and each eigenvalue is conserved integral. So, and you trace L to the k is some lambda e to the k. And it's obvious that since there are only n eigenvalues, when k is greater than n, it loses independence. Now I can tell you that in the those approaches turned out to be, first of all, these completely integrable systems. It's possible to solve them also quantum mechanically. Not only there was the huge theory of quantum integrable systems, which was the development of this thing. There are plenty of interesting, mostly two-dimensional equations which satisfy it. The most surprising thing is that this relation solves or describes so many physically important equations. For example, if you have the equation which appears, again, the equation appears in many places. It appears first in differential geometry, but then in the superconductors, it describes the Josephson effect and so on. It's the so-called Sine-Gordon equation. It's a relativistic equation for the field phi. It's a nonlinear equation, again with solitons, and again you can find this L and M. And there's no really general method to except the brute force to decide whether the equation is integrable. Usually if you have one extra integral, then it is integrable. To give you an idea, of course I cannot really do the calculations, but I'll give you an idea in the last minute. When we have the Toda case, this is, of course, the integral itself. It's the Hamiltonian. But there is also the first non-trivial integral. It begins with sum of Pn to the cube plus a lot of stuff. And you can discover it simply by trial and error. And then you start looking for the explanation. All In the 19th century, there have been several cases where integrability, some non-trivial integral of motion, appeared from nowhere. Just a few instances. One, for example, when you have a rotating top with a fixed point, so you have some body which rotates, then for general momenta of inertia, it's not integrable. However, Kovalevskaya found the case in which it is in which certain relation between moments of inertia which makes it integrable. By just by trials and errors, those integrals, trying this and that expression, it's a lot of hard work. Now we know that this integrability, this Kovalevskaya case for the symmetric top, can be solved in a few lines by using this commutator representation. Actually, on the other hand, so it's widely used in condensed matter physics, in material physics, in plasma physics. It's all extremely important set of equations which appears there. And it also is used in string theory and in gauge theories. In gauge theories, there's during the last 10 years or maybe less, there was people really found the analogs of L and M there, and it was great excitement because of that. Okay, I think that's time to stop here because you see it's open-ended. You cannot really. There's no natural boundary for this course except time. Let's stop here. Thank you very much.